Hi everyone. In this session we're going to take a look at sequential logic, and we're going to take a basic introductory look at hardware description language. So first off, we're going to look at sequential logic. Then we'll look at synchronous logic, followed by hardware description language. So we'll do an introductory look at what that is, and then virtual hardware description language, what they are, and we'll take a look at a basic example of that. And then some VHDL code that we'll kind of dissect from a very basic perspective to start with. Moving forward, we're going to go and write some of our own VHDL code. So first off, sequential logic. So sequential logic refers to digital circuits that generate output based on a combination of inputs and also past inputs. So on the other side of things, combinational logic depends on only the current state of the inputs. So sequential logic circuits that operate components under the control of a shared clock signal are referred to as synchronous logic. Okay, so we actually have a clock that is timing the process that goes forward from one logic circuit to the next. So it's a series of discrete operations under the control of the master clock signal. We talked a little bit about that in last week's material. So the processor maintains an internal state of information from one instruction to the next. So we basically cascade from one piece of logic to the next. So the next input is based on what the output of the previous input was. So modern complex digital service devices are almost always implemented as synchronous sequential logic devices. So that's why this discussion is very important. So gates, multiplexers, registers, and adders are usually what we call combinational logic circuits. And then these receive inputs under the control of synchronous logic, as we saw last week. So it's a combination of these two different processes, the sequential logic itself and the timing based on the clock, that makes it synchronous sequential logic. Now, logic diagrams, if we're building a computer architecture, these logic diagrams that we've seen, they become unwieldy pretty quick, which means they become quite large. So there has to be a better way to be able to create logic that we can work within our system. So a better way to do this is use what's called a hardware description language, or an HDL. Now, many have been developed over the years, and a developer can define a complex circuit using an HDL. So they can go into this programming language in a text editor, for example, write out the code for the processor that the logic that they want to create, and then it can be implemented, for example, on a chipset. So we can program it directly into a chip, and that makes it much more easier than having to actually write all of the logic flow diagrams. We can do this all within an HDL. So let's take a look at an example of a virtual hardware description language. So one of the most used hardware description languages today, basically just a simplified low-level programming language, right, is the VHSIC hardware description language, which stands for Very High Speed Integrated Circuit. So it's a very high speed integrated circuit hardware description language. So that's a mouthful. So the acronym then is VHDL for that. And it's based on a previously created programming language called Ada, which is based on Ada Lovelace, who was considered to be one of the first computer programmers. Another HDL is Verilog. So it's similar to VHDL in that we can write code that we can then programmatically use to create a chipset. Now we'll be using VHDL for our examples going forward, and let's just take a look at a basic VHDL example. So here's the full adder that we did previously. And I'm going to use my drawing pen that I have here. And we can see here that first off, we are defining what standard library we're going to use. So this is a standard. So any of the code that we create, any of the logic that we create after here should follow this particular standard. We don't need to know the details of this particular standard yet, but we should just know that the first thing we need to define is some kind of a standard that we're going to use. And then the next piece of our VHDL code here is the kind of construction of our full adder. And I'm going to show you a diagram of this full adder in a second. Okay, so that's our full adder. So this is basically just defining sort of two main things here. You can see here that we have three main inputs, our A, B, and C in. And again, I'll show you the diagram in a sec. And then we have two outputs. So an output S and we have an output C out. Okay, so this is defining the inputs and the outputs for our full adder logic. And then down here, we have the behavior of our full adder logic again. So our architecture, that the construction of how that full adder actually, how the logic works. So which logic gates are we going to use in this full adder? And you can see, for example, we have 1, 2 XOR logic gates. Here we have, and this is what we produce. These are the logic gates that we go through in order to produce our output S. And all of these are so we have an AND, an OR, an XOR, and another AND logic gate that will produce our C out output. So this is our first output S, and this is our second output C out. Okay, so I'm just going to turn the pen thing off, and then let's go to the next slide here. Okay, so first off, here's our standard libraries, like I was mentioning. The library we're going to use is it's from the IEEE, and the standard number for it is STD Logic 1164. And again, we don't know the details of that now. This is just a standard library. So any of the code that we create, again, should conform to this standard. Next, oh yeah, so the rules and the syntax is a very much more concise way of saying what I'm trying to say. Now here's our full adder with the inputs and the outputs. Okay, so I'm just going to get my drawing tool again here. And here you can see, like I showed previous, here's our three inputs. So A, B, and C in. And you can see over here, here's A, here's B, and here's C in. So there's our three inputs. Then our three outputs, sorry, our two outputs. And we can see over here, here's our S output, and here's our C output. So this particular entity, as it's called, describes the full adder, the inputs, and the outputs. Okay? So three inputs and two outputs, as I just mentioned. And then we define the actual behavior of the full adder. So you can see here, let me just go back. Actually, let's go here for a second. So here I have what the output will be to get to S. So with S as my output, I'm going to have first XOR A with B here. And then the output of A and B, I'm going to XOR with C. So whatever the output is here will then be XORed with C in order to produce the output S. And then the same thing for the logic with C out. But let's just follow this logic for S. So what I'm going to do is I'm going to turn off. You can see there's basically two XORs. The first one for A and B, and then the next one for C. And so let me go back then. Let's go back to the previous slide. And you can see here, if we look at that logic and we apply it here, you can see that A and B indeed are XORed. So here's our XOR gate here. And then the output of A and B is then XORed here with C. So the output here is then XORed with C here. And that gives us then the output of S. And then we can apply the same rule set to the output of C out. So the output of C out is a little bit more complex, right? Like we need to go through two AND gates and then an OR gate before we get our output, but the same idea. So we have to create this structure then. We have to model this structure, I guess is the best way to say it, in order to get the desired results using the VHDL code. Okay, so again, this is the same logic that we would apply here. All right, so we define the behavior of the full adder. Again, we don't need to understand it all yet. This is just our very basic first kick at it. But you start to get the idea that once we have an understanding of the logic, we can write that logic in code, and then that can be applied to our chipset. So we can build quite complex logic based on what we want our desired results to be. So that all describes then how the circuit logic operates. So all that we've created here then is from that full adder gate logic that we saw, that we went through previously. And once we have defined our inputs and outputs in our rules, then we can execute some code, right? And we'll look at this in more detail in the coming weeks. So this is our first introduction to it. We'll talk about it in much more detail as we go forward, particularly with the assignments. All right, so we looked at sequential logic, we looked at synchronous logic, and we looked at hardware description languages, a quick description of different ones that are available based on the Ada programming language. We looked at a virtual hardware description language, which we're going to cover in more detail. And then we just looked at a very simple full adder that we could implement using VHDL code. All right, so thanks for listening. We'll see you in the next session.